I handed out this last time. Does anybody need one? Anybody else need one? Absolutely. So, I guess going back, time back, we're just picking up where we left off last time. We kind of introduced this. Let me say this. I know this particular thing is boring. I know it. I know it's hard. You have to learn. You just have to. It's literally the thing that creates energy in the entire universe. Period. All the heat, all the light coming out off of our star, the fact that you can see any star anywhere, anytime, all has to do with this. It could be a whole lot worse. We're keeping it pretty simple, all told. We'll get in, we'll get out. When I'm done teaching this, and it'll be before the hour's over, if you want to go, you are welcome. It's no problem. If you want to stay because you want to understand more and you want to ask questions, you're welcome. That's no problem, okay? I won't be teaching this again after today. The video will be up on the website, on the Moodle. The video that I show you will be up on the Moodle. You've got this as a practice. I'll get another one of these up. The one up top is just it filled out completely. And then I give you 3 others just for you to practice. Like to be able to do this well, you need to be able to fill that in, right? And I put like things together, okay? I was very consistent. If it's a circle with a line around it, well, that's going to be a proton. If it's a circle without a line in it, well, that's going to be a neutron. If it's a little weird square thing, that's going to be a neutrino. If it's a hexagon, that's going to be a positron. If it's a triangle, that's going to be a gamma ray. Everywhere through the whole thing. As much as I can, I'm spoon feeding you, okay? You don't have to create this from blank. You don't have to memorize craziness. When you see that shape, you need to recognize, and you need to know what it is. You do need to understand that a gamma ray is just super high energy light. You need to know that a neutrino is a real particle. It has real mass. It's almost none. In fact, it's so small it travels just below the speed of light. And you need to know that it's neutral. It's in the name, neutrino, just like a neutron, right? Neutral. It has no charge, so it doesn't interact with stuff. Which is why, again, from last time, we calculated them. We knew there had to be something to account for this mass, but it was something so small and so inert that we couldn't have a way of measuring it. You need to understand that, and it's here, right? Just right away, you got 2 protons and they're colliding into each other because the center of the sun is so hot, right? It's got so much energy that it can cause these collisions, and that if it collides just right, it knocks off a neutrino, it knocks off a positron from a proton, and that proton becomes a neutron. And you stick together a proton and a neutron, and so it has a charge of just +1, but it has a mass of 2. That's called a deuteron. But at any rate, let me begin with some prayer, and we'll go from there, okay? Heavenly Father, please just help me to be simple and to be clear. Help me to preach this with as much energy and enthusiasm for something that's very difficult but very wondrous as I possibly can, Lord. Let this not be boring for us. Let us take interest in knowing truly that this is how you've ordained the entire universe to work. This is where we get energy from. Help us to learn it well, learn it thoroughly, learn it clearly, for our good and for your glory. We pray this in Jesus' name. Amen. All right. Let's do a quick review. I told you there are 4 particles. Well, there's more than 4 particles, right? We talked about matter and we talked about antimatter. Give me 3 most fundamental particles of matter. Proton,
Neutron.
neutron,
Electron.
electron. What's the equivalent of a proton in terms of antimatter? You gotta speak up. What'd you say it is? Antiproton. I'm hard of hearing, man. That's all there is. Antiproton. Okay? And the equivalent of an electron?
Positron.
Positron. By the way, did I mention this stuff is as hard as it gets, okay? The stuff we're doing today, this course is front-loaded with difficulty. It's really hard out of the gate, and then it coasts, okay? So just, if you can get through this, you're gonna be great. So, what's the difference between a proton and an antiproton?
Charge.
Charge. What about mass? Any difference in mass? No. No. What's the difference between an electron and a positron?
Charge.
Charge. Mass? No, same mass. Same mass, right? But the charges are different. When matter is created, it's always created one particle of matter, one particle of antimatter. Always. If I make a proton, I've got to make an antiproton. I don't have to, but that's how it happens. If a positron is created, then an electron is created. Always. What's wild about that we talked about last time, is that these particles, these pairs of particles, they have opposite charges. So what do? Attract. So as quickly as they're made, they would be destroyed. They would annihilate each other and come back into producing energy again, right? Which means that for every particle of matter, should be a particle of antimatter, which means either there should be equivalent amounts somewhere, somehow being held apart, or they should all be colliding back in together and there should be nothing, but we should see almost anything except for what we do see. What do we see? Matter. You see all this matter and not this antimatter. Scientifically, not possible. This is, later on, at the end of the year, your final exam is going to have to do with just the one, essentially, how does this class relate to, and I'm going to point you to some Psalms in particular, about God's hand in creating the universe. Something like this would be a good thing to talk about, right? I mean, my goodness, this is, for many people, this is a proof that God exists. Because this can't exist without a God, as far as anything we understand about the universe. Okay, now, I'm not just talking to you about this because I'm trying to convince you that there's a God. I hope that this does do that, but I'm teaching you this because we are dealing with this, this, and this, and this. Right? Not so much that. But these things are represented on this sheet of paper, right? So we need to know what they are. And there's one more, right? And it's a neutrino. Do they have mass? Say yes, but I mean it's like, it's so tiny. Do they have charge? No charge. Super small, super fast, no charge, they don't interact with other stuff. I'm sure I told you last time, you have just trillions and trillions of them, not only coming at you right now, but they're passing right through you. They're passing right through, completely unaffected by anything. And you don't even know it. Okay. Fusion. Nuclear fusion. What temperature do we need for nuclear fusion to occur?
At least 12 million.
At least 12 million degrees. You can say Kelvin, you can say centigrade, okay? You don't need to, I don't care about the 273.15 difference. But it's hot, right? Fusion. Just think of the root word of fusion. What's the one word at the core of it?
Fuse.
To fuse. What do you do when you fuse something?
Put together.
Put it together. What are we putting together? Hmm?
Gas and plasma.
Yeah, gas, plasma. What part of the gas in the plasma?
Hydrogen.
Yeah, we're gonna make, essentially what's happening when we talk about fusion, what we're describing is how you turn lighter elements into heavier elements. The fusion in particular that we're talking about is how you make helium, for this, is how you make helium out of hydrogen. But when we talk about fusion in general, it doesn't have to be hydrogen into helium. Every element on here is a result of fusion. You can't have xenon without adding smaller parts together. How do you do that? Well, think about it. You've got things that have a positive charge that you're going to have to be able to stick together, and they don't want to, right? You have to have a whole lot of energy. You have to have just the right angle, just the right velocity, just the right circumstance, just the right pressure, just the right everything to get them so close and just right that they stick, that the strong nuclear force takes over and holds them together instead of them merely flying apart like two magnets, right? That's what we mean when we say fusion. And it requires a minimum of this. This is what it takes to make helium. You want to make something like iron, you got to get a whole lot hotter. It takes a whole lot more energy, okay? You want to make something heavier than iron? Let me show you what I mean by that. So iron, iron's here, right? Okay, our star will never make iron. Our star at the very, very end of its life can make up to carbon, right? So you're going this way, this way, this way, and we can make up to carbon. To make anything as heavy as iron, though, you've got to be huge. You've got to have so much energy, so much heat. But to make anything heavier than iron, iron's the limit. Because every other atom below iron, when you make it, it releases a little bit of energy. Okay? It takes energy to make it, but it releases more energy than it takes to make it. Iron, it takes more energy to make it than is released by it because it's so stable. So iron's the limit. In any star, any giant star, a blue giant, a red giant, they can't make anything heavier than iron. It's the limit. Because once they start making iron, all their energy goes into making iron and the star just begins to die. So how do we get anything heavier than iron? In a supernova. Why am I telling you all that right now? On day 4, whatever this is. Because fusion requires tremendous amounts of energy. Okay? And the larger the atom that we're going to try to make, the more energy that's required. Right now, our sun is at 15 million degrees centigrade, which is well above the 12 that's required to make helium. It's not nearly hot enough to make other things, though. Okay? All right. So fusion, we're producing. We give you just a good functional definition of fusion. Heavier elements from lighter elements. That is pretty well done. So the first thing that you've got to do is you've got to have two protons. These are two hydrogen nuclei, right? Hydrogen atomic number 1. When you have all your life, if you've in any kind of chemistry or anything else, whenever you've done hydrogen, you've probably done something like this. All right, what did I just draw there?
Atom.
It's an atom. What are the parts of the atom that you see there?
Proton.
I got a proton in my nucleus, and what's going on outside of it?
Electron.
An electron. What's missing?
Positive.
What's missing here?
Electrons.
I don't have any electrons. Why don't I have any electrons?
So hot the electrons are kind of.
Yeah. So, as a solid, as a liquid, as a gas, you've got electrons going around your nuclei. You know that as you get warmer, you move from a solid to a liquid, right? That energy results in molecules flowing freely. Then, as I heat up even more, I can go from a liquid to a gas. And now they're really flowing freely, right? And you've heard of the word plasma, but do you know what it is?
It's hotter than gas. It's like more free flowing.
But what makes it plasma? What's the difference between plasma and just at some point, we add one more joule of energy and we cross from a gas to a plasma, but what happens? This has too much energy. There's too much heat for that electron to continue around the nucleus. So somewhere on the side, you want a good definition of this. We'll come back to it and you can ask me later, but basically, what is plasma? Okay? I'm going to kind of write it up here. What is plasma? The answer is it's ionized gas. And if that doesn't make sense, then you've got to ask the question, well, what is ionized gas? It's gas that it's so hot that the electrons can't stay. The electrons fly off apart from the nuclei. Too hot for electrons to stay put. Okay, that's all plasma is. If you've been around ranches or any of that kind of stuff for welding, and you need to cut really thick metal, what tool do you use? I know.
Plasma cutter.
Plasma cutter, plasma torch, right? In the name, it's telling you that's plasma. So what do you know about it? It's so crazy hot that the electrons cannot stay around the atoms, right? Wildly hot. That's some serious stuff. Okay, so here we are, we're in fusion, we're dealing with plasma. It's so hot that my electrons cannot stay around the nuclei. So let me get rid of this. Right? Start with 2 protons. Why 2 protons? Because this is the thing that the whole universe is made up of. Do we have other stuff? Absolutely. But we got a whole lot of this. In fact, our sun, I think it tells you on here. Somewhere on here it ought to tell you about how much of our sun is hydrogen. Take a look. About 75%. At one point, theoretically, it would have been 100%, right? So about, a certain percentage of it has been burned up and it has been produced into helium. You start with hydrogen, and those hydrogen at above 12 million degrees will have collisions. Most of those collisions, they just bounce off of each other. But if they hit at the right angle, then they stick. And when that's what you have drawn here in that first thing. You don't necessarily have to draw a thing right now, right? You've already got everything I'm doing. I'm just trying to break it down and ask questions, okay, if it doesn't make sense. When they hit, there's a collision, okay? And in that collision, one of them is going to remain a proton, the other one gets the snot knocked out of it, right? Literally, it gets a little tiny bit of mass. What is this V? Does yours say? Does it not say?
It says a V.
Just says a V? Okay, you got to know this. This is a neutrino. Label that. This is exactly what you're going to have to be able to do on a test. I'm going to go, hey, what is V? And you're going to say, that's a neutrino. It's going to knock off this little tiny chargeless bit of mass. And that, right now, I told you that neutrinos are flying at you so fast from the sun, that's because this is happening. They just shoot off in all directions. So a neutrino, a little tiny bit of mass, flies off. That's why a neutron is just ever so slightly less massive than a proton is, okay? I'm gonna put it in here for a neutron, right? Because that's what this is. So a little bit of mass gets knocked off, and also the charge gets knocked off, right? What's the charge on a proton?
Positive.
Positive. A neutron is neutral. The positive has to go somewhere. It is a positron, right? So we emit a positron. Okay? That positron comes flying off. What's the charge? Positive. Here we are in plasma. There's electrons everywhere. They're just not bound to nuclei, but they're everywhere. This is positive charge. It's charge on an electron.
Negative.
Negative. They're attracted. They don't have to try very hard. They are going to be magnetically drawn towards each other. Nearly instantaneously. As soon as this positron is emitted, it crashes into an electron. And when that happens, they annihilate each other. And what is produced? I'm sure it looks like this on yours. Does it look like a weird little Y on yours?
Yeah.
That's the Greek symbol gamma. This is for gamma ray. Emits 2 gamma rays. I'm going to erase this for a moment, and we're going to talk about light. What is light?
Energy.
It's energy. Right? How does it travel? What does it look like when it travels?
The wave.
It looks like a wave. True or false? All light travels at the same speed.
False.
True. No, it's true.
That's right. It's the
Speed of light. All light travels at the same speed. True or false? All light has the same amount of energy. Name light that's dangerous for you.
Gamma rays.
Gamma rays surely are. What else?
X-ray.
X-rays, definitely. What else?
Ultraviolet.
Ultraviolet, right? Skincare products for that stuff, right? You don't want to get skin cancer. Cover up when you go outside. Not because you're worried about gamma rays, just because you're worried about UV. UV relatively is not that energetic. It has more energy than red, yellow, orange, blue, indigo, violet, but not as much as X-rays or gamma rays. Name some light that's no problem to you.
visible light.
All the visible light. Doesn't cause you a problem at all. What else? There's a lot of light you can't see.
Infrared.
Hmm?
Infrared.
Infrared, not a problem.
Microwave.
Microwaves.
There's one more. Radio waves.
Radio waves. Very good. Did you say infrared? You did.
I said those.
Okay, good. All right. So there's a lot of different energies of light. But they're all traveling at the same speed. So they all have the same speed, but they have different energies. What makes one more energetic than the other? Where's the energy at?
Frequency.
I'll buy that. I was looking for wavelength, but they're,
Yeah.
they're related. So here's the deal. Something like a radio wave has a very, very long wavelength. Very long. It's traveling very fast, but it's while it's traveling, it's just kind of leisurely making this motion. Something like a gamma ray would be more. I mean, I used to do this. Of course, I had a lot more board space when I used to teach, but. Well, just give me, Cody, come up here. You're going to be a radio wave, okay? You and I are going to travel at the same speed. Okay? But I'm going to have a whole lot more energy. And we're going to demonstrate to everybody the difference. You're going to have your arm out here, your finger's going to be the radio wave, and you're just going to walk nice and leisurely like this, okay? So between 1 and 3 meters long. You ready? Yep, okay. And I'm going to be kind of here, and I'm going to be going at the same pace as you. We're going to walk the same pace. You better go ahead of me, I got to follow you. But I'm going to be a gamma ray. I'm going to have a whole lot more energy. You ready? Go. Go faster. It's awkward. We're going at the same pace, right? But I'm going up and down and up and down, 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 like crazy. While he's just really going like, right? The energy is in that wavelength. That's where the idea of frequency comes.
Frequency is the opposite idea.
Pardon?
Frequency is the opposite idea.
Right. Exactly. So, when we talk about light, typically what you'll see is something like this. We'll draw like, everything from down here radio, over here gamma. You go, we go radio, micro, infrared, and then we go red, orange, yellow, green, blue, indigo, violet. Then we have UV. Then we have X-ray, and then gamma ray. They're all traveling at the same, but they have very different energies. And you can see it. This, you use your phone. Your phone's shooting out radio waves all the time. You listen to a radio. The radio's picking up radio waves all the time. It doesn't faze you, not at all. Totally fine. Gamma rays have so much energy, they will penetrate right through you. They can hit your cells. They can hit your DNA. They can cause DNA to blow up and recombine. You can get cancer from it. UV can hit your DNA, penetrate through, hit your DNA, cause it to break apart, recombine. You can end up with skin cancer, right? So, all this about light, and we'll come back to this later on. We're talking about stars. We can't go visit one. All we can do is look at them with light, and a lot of we can't see. We can't see this part of the light with them, and yet we can see them, which is kind of cool. It's because we're seeing them in different wavelengths. But all this was so that you go, hey, gamma rays. It's light, incredibly, incredibly high energy light. What happens in fusion is we convert matter into energy. What's the famous formula? E equals mc squared. Look, you're taking these two things and slamming them together. They disappear and they just turn into energy. That's E equals mc squared, right? Okay? The energy is in the form of light. It's coming from the matter, from a little tiny bit of positron, combining with an electron, and producing 2 gamma rays. So if I can combine a positron and an electron and make 2 gamma rays, then the opposite also must be true by E equals mc squared. I must be able to take 2 gamma rays, and if I can slam them together just right, then out of nowhere would come 1 positron and 1 electron. And guess what? We've done that. They can do that with the right machinery. Okay? All right. Which is how they know that when you do that, you always get one of one and one of the other, by the way. Any questions so far? Why are you not as excited? I'm like out of breath. Why are you not excited about this? Okay. So 2 protons come together. Right away, it knocks off a neutrino and a positron. Right? A little bit of mass and some charge. This thing has mass. It has more mass than the neutrino does. That combines with an electron, and it produces light. Do yourself a favor, somewhere write this first step is so critical. Explain that to yourself so that later on it makes sense. You put it in your words. 2 protons slam into each other, it knocks off a neutrino and a positron. which immediately combines an electron to produce light. These are the symbols that you see on that sheet. What's the positive sign? It's just a proton, right? Any of these you don't know, I'd write them down. What is this?
It's a neutrino.
It's a neutrino. An E with a plus.
Positron.
It's a positron. The Y.
Gamma.
Gamma. Gamma ray. E with a negative. Electron. H with a 1 by it.
Hydrogen.
It's hydrogen with a mass of 1.
Hydrogen without neutrons.
H with a 2 by it. It's hydrogen with a mass of 2. One of those comes from a proton, one of those comes from a neutron. We call this a deuteron. It equals a proton plus a neutron. Okay? He with a 3. What is it? Not hydrogen this time. Helium. This is what we refer to as light helium, by the way. Not that you have to know that, but it's what you just need to know here is it's helium with how many protons? Yeah, by definition, to be helium, it's got to have 2 protons, right? With 2 protons and 1 neutron. And then this last one, 4He, this is helium with 2 protons and 2 neutrons. If you got that, you got it made, man. I'm gonna draw some stuff. I want you to tell me what it is. All right, what's number 1?
Gamma ray.
Gamma ray. What's number 2? What is it? Proton, also called
Hydrogen.
hydrogen. What's number 3?
Helium-4.
Helium-4, good. What's number 5? Or no, what's number 4?
Helium-3.
Helium-3, good. What's number 5?
Hydrogen.
Helium, well, it's hydrogen 2, but what do we call that? It has a name. A deuteron. Good. Deuteron. What's number 6?
Positron.
Positron. What's number 7?
Electron.
Electron. What's number 8?
Neutrino.
Neutrino. All right. Those are all those are the things that we're going to see on this. Nothing else. Okay. So all that so we can get back to step number 1. Step number 1. These two things collide. Neutrino gets knocked off. Positron gets knocked off. Because of opposite charges, it immediately combines an electron, produces 2 gamma rays through annihilation. This is E equals mc squared, right there. We converted mass into energy right there. And this is what's powering the universe. Where'd my sheet go? Okay, now, the next step. Next step is that this thing, moving it forward, right? Same thing. It gets struck by another hydrogen. Okay? When that happens, this time it doesn't release any particles, but it does release energy. Energy in the form of what? A gamma ray. Okay. And so at the end of that, I've got this. What is this? Helium. It's light helium, right? Helium-3. Okay. So this happens. At the end of this first part of the chain, you get light helium. I have to have another one of these, another light helium. That's why on these it's showing you two chains of this happening, okay? When I get another light helium, if these two crash into each other just right, then I get another major reaction, okay? And at that point, I will get this. So what happened there? Two heliums went flying, right? Or 2 hydrogens went flying off, right? So here I had 2 protons and a neutron, 2 protons and a neutron. If you do the math on that, it's 4 protons, 2 neutrons. That's not going to turn into helium, right? If that actually stuck together, that would be beryllium. But they don't stick together. When they crash together, it'll form the helium that I'm looking for, that I'm expecting, but it will also shoot off 2 protons. So this is called the proton-proton chain reaction. I know it's not exciting, but it is incredibly important. When we talk about fusion in this class, and what's going on in the core of a main sequence star, this is it. Okay? Again, your goal is to understand each of these symbols, and given a drawing like this, to be able to label it. Or if I give you this drawing, to be able to tell me what every symbol is. You know, if I go, hey, what's happening at this step, or this step, or this step, you should be able to tell me what the particles are. Okay? Let me show you two things, and then if you want, we can be done. Y'all want to see the proton-proton chain video again from the guy the other day, or do you want to not? Because I already bored you enough.
We good?
All right, will not. Let me show you neutrinos now, okay?
Get in the group.
This video is sponsored by Masterworks. The image that you're looking at is that of the sun. But here's the astounding part. It was not taken looking up at the sky, but taken looking down at the earth. How the heck is that possible? Well, this is a photo of the neutrino emission of the sun. Neutrinos are so small and interact so little with other particles that nearly all of them pass right through the 12,700 kilometer diameter of the Earth without hitting a single atom. The sun produces a mind-boggling 10 to the 38 neutrinos every second. In fact, 100 trillion neutrinos are passing through your body every second right now. Don't be alarmed though, they're harmless. You can't feel them whatsoever because they're not interacting with anything. They're kind of like a ghost that can pass right through walls. In fact, it's estimated that a single neutrino could pass through a 1 light year thick chunk of lead without hitting anything. So the question you might ask, if they don't interact with anything, what purpose do they serve? Nothing is built from these particles. They're seemingly useless. Yet, they're everywhere. And in fact, you wouldn't exist without them. How can this be? What are these ghost particles and what purpose do they serve in the workings of the universe? That's coming up right now. I think you're going to be fascinated by the story of neutrinos, which you'll find are really responsible for everything. But before I get into that, I want to acknowledge Masterworks for sponsoring this video. It's been a tough year headline. And although they may appear to serve no useful functions, they are in fact very important. For one thing, they're ubiquitous. They are the second most abundant particles we know of, after photons. When a supernova explodes, 98% of the energy is carried by neutrinos within the first 10 seconds, not photons, as you might have thought. They don't carry a charge, and they interact very weakly. This is why they can go right through the Earth without interacting with anything. You might ask, if they go right through the Earth, right through our bodies, then they probably go right through our instruments. So how the heck did we ever know they even existed? Well, they were first theorized in 1930 by none other than Wolfgang Pauli, who is perhaps most well known for the Pauli exclusion principle. He was trying to solve a known conundrum in physics at the time. The conundrum was that some of the energy in a radioactive beta decay appeared to be missing. A beta decay occurs when an atom has too many neutrons or protons in its nucleus. When there are too many neutrons, the nucleus becomes more stable by transforming a neutron into a proton. This is called a beta minus decay. This process emits an electron. Scientists had noticed that the electron which was emitted did not always have the same energy. Sometimes it had more and sometimes it had less. But since the proton always had a fixed value for its mass, they couldn't understand how the electron's energy varied. This appeared to violate a sacrosanct principle in physics, the principle of conservation of energy. Pauli proposed that perhaps a second invisible particle was being emitted along with the electron, which carried the different energies, allowing for overall energy to be conserved. But if it existed, it became clear that it must be neutral in order to conserve charge, be very light and weakly interacting, because it was not easily detected. Enrico Fermi soon after coined the term neutrino for this as yet undiscovered particle. Now the question you have to ask, how were they experimentally detected if they don't interact with anything? Well, what's favorable for detection is the fact that they are so extremely abundant, to the tune of 100 trillion going through your body every second. It turns out that if you build a detector large enough and leave it on for long enough, A small percentage of these neutrinos will interact often enough that we can detect them. In fact, they were confirmed experimentally in 1956, 26 years after first being theorized, by physicists Fred Rines and Clyde Cohen, for which a Nobel Prize was later awarded. Their detector weighed 10 tons and was placed near a powerful fission reactor. The fission and fusion processes produce a lot of neutrinos. For example, the tremendous fusion reaction inside stars like our sun is the reason these particles are so abundant. How are they produced in the fusion process? When the sun fuses hydrogen to helium, this is a multi-step process, the end result of which turns 4 protons into a helium nucleus consisting of 2 protons and 2 neutrons. This process produces 2 positrons and 2 neutrinos. Now you might say, if that's the case, we should be as bombarded with streams of positrons as we are with neutrinos. Why doesn't that happen? The reason is because neutrinos don't interact with anything and pretty much pass right through the sun and onto the Earth. The positrons, on the other hand, being the antiparticle of electrons, are immediately annihilated by electrons in the plasma of the sun to produce high-energy photons, or gamma rays. But by the time they make it out of the sun's core, we see them as mostly visible light. So we should be thankful that we are bombarded by visible light instead of positrons or gamma rays. The neutrino emission from the sun is where this particle gets a little weird, and the mystery of its mass comes about. They were initially thought to be massless, but we now believe that they do have mass because the neutrinos from the sun went missing. What do I mean by this? We know how many neutrinos are supposed to be produced by nuclear reactions in the sun, and these can be detected right here on Earth. However, we didn't detect nearly as many neutrinos as we should have. This was called the solar neutrino problem. So where did this missing neutrino go? Well, it turns out that neutrinos, like all fermions, actually come in 3 different types, called flavors. The flavors are electron neutrinos, muon neutrinos, and tau neutrinos. Electron neutrinos were the ones we were looking for. But when we learned how to detect the other 2 flavors, muon and tau neutrinos, suddenly the missing neutrinos could be accounted for. Somehow they changed from electron neutrinos to muon and tau on their way here from the sun. This changing of flavors can only happen if these 3 particles have a non-zero mass. Now, what do flavors have to do with their mass? Well, this is where the weirdness comes from. I'll give you the simple answer, then I'll give you the more complicated answer. The simple answer is that in order for flavor change to happen, some passing of time must occur for the particles. In other words, if no time passed for the particle, then no change could happen. But since flavor change does occur, time must be passing for them. If time is passing for them, then they must be traveling less than the speed of light, because at the speed of light, no time passes, as is the case for photons. Now, if they're traveling less than the speed of light, this means they must have some mass, because physics dictates that if they had no mass, they must travel at the speed of light. Now, here's the simplified version of the more complicated answer. Remember the uncertainty principle in quantum physics, where a particle cannot have a precise position and a precise momentum at the same time? That is, when a particle has a well-defined position, then it will not have a precise momentum. And when it has a well-defined momentum, it doesn't have a precise position. In other words, if we know how fast it's going, we don't know where it is, and if we know where it is, we don't know how fast it's going. Something similar seems to be going on with neutrino mass and flavor. When a neutrino has a precise mass, its flavor is mixed. When it has a precise flavor, its mass is mixed. So what appears to be happening is that on its way to Earth, the neutrino is in a kind of superposition, or a mixed state of various possible masses and flavors. This is called neutrino oscillation. Unlike the uncertainty principle, there's no reason why we should not be able to measure the mass of the neutrinos. In principle, the mass could be measured, but they're just so light and non-interactive that we don't have a way to pin down its masses precisely, at least not yet. The probability of it flipping or oscillating between the electron and muon neutrino flavors can be precisely calculated, and observations confirm this. The source of this neutrino mass, and hence the oscillation, is the mystery. We don't know why they oscillate, and this needs to be explained. But because this flipping or oscillation occurs, we know there must be some mass, even though we don't know the mechanism of this mass. We just know that there are 3 neutrino flavors and 3 neutrino masses. We also know that the electron neutrino mass cannot be more than about 0.8 electron volts, which is on the order of a millionth of the mass of the electron. Now, you might say, why is the mass a mystery? Why can't we explain it using the Higgs field, which is the source of mass for all the other massive elementary particles? In order to understand why, I have to explain in a simplified way how the Higgs field confers mass. We can consider that the Higgs flips the handedness or chirality of fermions if it interacts with them. So when we say that the mass of the electron is created by its interactions with the Higgs field, we can think of this as the Higgs field rapidly changing a left-handed electron into a right-handed electron and vice versa. This switching back and forth is energy. And because energy and mass are equivalent via E equals mc squared, this energy shows up as its rest mass. A heavier particle, like the top quark, would experience this flipping at a much higher frequency than a lighter particle like the electron. And that's why it would have a higher mass. This mechanism, however, doesn't work for the neutrino because it stays in its left-handed state forever. Right-handed neutrinos don't exist, or at least we've never detected them. So this is why they're thought not to interact with the Higgs. So the source of the mass of the neutrino remains a mystery and seems to point to new as yet undiscovered physics. And it confirms that the standard model is incomplete, which is not a bad thing because this could be an exciting area of research for future physicists.
That's enough. We probably could have stopped 3 minutes ago. Anyway. Most of you probably went, that was dumb. I didn't care anything about that. And that's fine. Some of you were like, what the heck's a neutrino? And that scratched an itch for you. Wasted your time, well, it wasn't that long. So I am here. If you want to ask questions, go over anything, review anything, I will be here. If not, your time is yours. God bless.